In this video, we will learn about the Zener diode and we will see that how the Zener diode can be operated as a voltage regulator. Now in the previous videos, we have seen that how this PN junction diode can be operated in the forward as well as in the reverse direction. And we have also seen that in case of a reverse bias condition, when the applied voltage is less than this breakdown voltage, then there is hardly any flow of current through the diode. But as soon as the voltage across the diode is more than this breakdown voltage, then suddenly a lot of current starts flowing in the reverse direction. So this region of operation of the diode is known as the breakdown region of operation. And for a normal diode, this region of operation should be avoided. But there are some diodes which are meant to be used in this breakdown region. And these diodes are known as the Zener diode. So here is the symbol of the Zener diode. And if you see the VI characteristic of the Zener diode, then it looks quite similar to the normal diode. So as you can see, in the forward bias condition, it just works similar to the normal diode. And in the reverse direction, when the applied voltage is more than the threshold voltage, then suddenly the diode starts operating in the breakdown region. So the voltage after which the Zener diode operates in this breakdown region is known as the Zener voltage. And the corresponding current which is flowing through the Zener diode is known as the Zener current. Now unlike the normal diodes, this Zener breakdown voltage can be as low as 2 volt or as high as 200 volts. But if you see the normal diodes, typically the breakdown voltage used to be more than 20 volts. So unlike the normal diodes, these Zener diodes are heavily doped. And by changing the doping concentration, we can change the Zener voltage of this Zener diode. So for the Zener diodes, where the breakdown voltage is less than 4 volt, the Zener effect is the predominant effect. On the other end, for the Zener diodes, whose breakdown voltage is more than 6 volt, the avalanche effect is the predominant effect. And we have already discussed about these two effects in the previous video. So for more information, you can check that video. But irrespective of the breakdown mechanism, all the diodes which are meant to be used in this breakdown region are known as the Zener diodes. Now in this Zener diode, in the reverse bias condition, when the applied voltage is more than the Zener voltage, then this Zener diode will operate in the breakdown region. And if there is no current limiting resistor in series with this Zener diode, then suddenly an excessive amount of current starts flowing through this Zener diode. And in a way, because of the excessive power dissipation, this Zener diode may get damaged. So to limit this current, it is required to connect a current limiting resistor in series with this Zener diode. And if you see the datasheet of any Zener diode, then you will find that the maximum Zener current is defined for the every Zener diode. It means that the maximum allowable current through the Zener diode should be less than this current. And if you see the datasheet, one more current is also defined for the Zener diode, which is known as the minimum Zener current. So basically, this current defines the minimum current which should be required to use this Zener diode in this breakdown region. So whenever the Zener diode is used in this breakdown region, then the operating current of the Zener diode should be between these two limits. So for any Zener diode, when the applied voltage Vs is more than this Zener voltage and the operating current is in between this IZK and the IZM, then we can say that the Zener diode is operating in this breakdown region. So now if you see the voltage characteristic of the Zener diode, then you can see that even if we go beyond this Zener voltage, then also there is hardly any change in the voltage across this Zener diode. Or in other words, we can say that the voltage across the Zener diode remains constant. So in a way, this Zener diode can be operated as a voltage regulator. So in the first approximation, we will assume that whenever the voltage across the Zener diode is more than the Zener voltage, in that case, the Zener diode can be replaced by a constant voltage source of Vz. But in reality, if you see, this curve is not a straight line. It means that this Zener diode should have some series resistance, and this series resistance is known as the Zener resistance. So because of this Zener resistance, if the current which is flowing through the Zener diode will increase, then the voltage drop across this Zener resistor will increase. And due to that, the overall voltage which appears across the Zener diode will increase. But here for our analysis we will assume that the Zener resistance of the Zener diode is 0. Apart from that we will also assume that the Zener current IZK is equal to 0. That means in the reverse bias condition the current which is required to turn on the Zener diode is also 0. So under these assumptions, now let us see how the Zener diode can be operated as a voltage regulator. So under this approximation, if the supply voltage Vs is more than Vz, in that case the Zener diode will operate in the breakdown region and it will provide a constant voltage Vz across the two terminals. So in a way we can use the Zener diode as a voltage regulator, and this is particularly useful for designing the power supplies. So let's say we are designing the power supply using the full wave rectifier circuit, and for the filtration here we are using the capacitor filter. Now if you recall, even if we use this capacitor filter, then also there is some finite ripple in the output waveform, and this ripple can be further reduced if we use this Zener diode at the output of this capacitor filter. So in this way this Zener diode acts as a voltage regulator and it provides a constant voltage across the two terminals. Now here even if we connect the load resistance across this Zener diode, then also it will provide a constant voltage across this load resistance. But now whenever we connect this load resistance, then first of all we need to find the Thevenin's equivalent voltage across these two terminals, because under the no load condition whenever we apply the supply voltage, then the entire voltage is appearing across this Zener diode. But when we connect this load resistance RL, then first of all we need to ensure that the voltage across these two terminals is more than the Zener voltage. So to find this voltage across this Zener diode, first of all we will find the Thevenin's equivalent voltage across these two terminals, and it can be given as RL divided by RL plus RS times Vs. Now if this Thevenin's voltage is more than Vz, in that case this Zener diode will operate in the breakdown region. So if this Zener diode operates in the breakdown region, then it will provide a constant voltage Vz to this load resistor, and in that case the load current IL will be equal to VL divided by RL, and here VL is nothing but the Vz. That means the load current IL will be equal to Vz divided by RL. Similarly, now let us see what is the source current or the series current which is flowing through this resistor RS. So this source current IS can be given as Vs minus Vz divided by RS. So this is the source current which is supplied by this voltage source. So now we know the source current and this load current, and the remaining current will flow through this Zener diode, and this current is known as the Zener current. So if we apply the KCL at this node, then we can say that this current IS is equal to IZ plus IL, or we can say that the Zener current IZ is equal to IS minus IL. So this is the current which is flowing through this Zener diode, and the power which is getting dissipated across the Zener diode is equal to Vz times Iz. So basically it is the product of Zener voltage and the Zener current. So in this way we can find the Zener current through the Zener diode. So let us take one simple example so that this concept will get clear to you. So in this example we have been asked to find the Zener current and the power which is getting dissipated across this Zener diode. So first of all we need to ensure that the voltage across the Zener diode is more than 10 volt. So for that we will find the Thevenin's equivalent voltage across these two terminals. So here this VTH can be given as 1 kilo ohm divided by 1 kilo ohm plus 250 ohm times 18 volt, and if we calculate the value then it will come out as 14.4 volt. So as this Thevenin's equivalent voltage is more than 10 volt, so this Zener diode will operate in the breakdown region, and it will provide a constant voltage of 10 volt across this load resistor. So from this we can say that the load current IL will be equal to 10 volt divided by 1 kilo ohm, which is equal to 10 milliampere. And here the series current IS or the source current IS will be equal to 18 volt minus 10 volt divided by 250 ohm, and it will be equal to 32 milliampere. So this current IS is equal to 32 milliampere. Now we know that Zener current IZ can be given as IS minus IL, that is equal to 32 minus 10 milliampere, which is equal to 22 milliampere. So this is the Zener current which is flowing through this Zener diode, and the power which is getting dissipated can be given as IZ times Vz, that is equal to 22 milliampere times 10 volt. So the power which is getting dissipated across this Zener diode is equal to 220 milliwatt. So in this way we can find the Zener current as well as the power dissipation. Now whenever the Zener diode is used as a voltage regulator, then depending on the application, the supply voltage or the load resistance will change. But despite the change in these parameters, this Zener diode should provide a constant voltage across the load, or in other words, it should work properly as a voltage regulator. So in general we can say that whenever the Zener diode is used as a voltage regulator, then there are three variables. One is the supply voltage, and the other one is the load resistance, and the third variable is the series resistance. So here what we will do, we will consider the two parameters constant, and we will assume that the third parameter is a variable, and we will find the maximum and the minimum value of this parameter such that the Zener diode will operate in the breakdown region, or in other words, this regulator circuit will work properly as a voltage regulator. So first of all we will assume that this supply voltage Vs and this series resistance Rs are constant, and the load resistance RL is variable. So we will find the minimum and the maximum value of this load resistor such that the Zener diode will work properly as a voltage regulator. So first of all, let us find out the minimum value of this load resistance. And to find that, first of all, let us write the Thevenin's equivalent voltage across this Zener diode. So this voltage VTH can be given as RL divided by RL plus RS times Vs. Now from the equation, if you observe, as the value of this load resistance RL reduces, then the Thevenin's equivalent voltage across these two terminals will reduce. But if this Thevenin's equivalent voltage goes below this voltage Vz, in that case this Zener diode will come out of the breakdown region. So the Thevenin's equivalent voltage should be at least equal to Zener voltage, and from this we can find the minimum value of this load resistance. So if we equate this expression with Vz, and if we rearrange the terms, then the minimum value of this load resistance can be given as Rs times Vz divided by Vs minus Vz. So this will be the minimum value of the load resistance to ensure that the Zener diode works properly in the breakdown region. Similarly, now let us find out the maximum value of this load resistor. Now whenever this load resistance RL is maximum, at that time the current which is flowing through this load is minimum, or in other words we can say that the IL minimum will be equal to Vz divided by RL maximum. Now here, as the Vs and Rs are fixed, so the value of current Is will be fixed. So this current Is can be given as Vs minus Vz divided by Rs. So this current Is will remain fixed. Now as we increase the value of this RL, then the current which is flowing through this load resistor will reduce, and at the same time the current which is flowing through the Zener diode will increase. So as we keep on increasing the value of RL, then the current which is flowing through the Zener diode will increase. But we know that current which is flowing through the Zener diode should be less than the maximum rating, or in other words it should be less than IZM. So whenever the maximum current is flowing through the Zener diode, at that time the current which is flowing through this load RL is minimum, or mathematically we can write it as Is is equal to IZM plus IL minimum. That means the IL minimum is equal to Is minus IZM. And from this we can find the maximum value of this load resistor. So to understand it better, let us take one example. So in this example, we have been given this Zener regulator circuit and we have been asked to find the minimum and the maximum value of this load resistor. So first of all, let us find the minimum value of this load resistor. And we know that the minimum value of this load can be given as Rs times Vz divided by Vs minus Vz. And if we put the values, then we can write it as 100 ohm times 5 volt divided by 5 volt. That means the minimum value of this load resistor is equal to 100 ohm. Similarly, now let us find out the maximum value. So for finding the maximum value, first of all we will find the source current Is, and the source current Is can be given as 10 volt minus 5 volt divided by 100 ohm, that is equal to 50 milliampere. So this is the source current which is supplied by this 10 volt source, and from this we can say that the IL minimum will be equal to Is minus IZM, that is equal to 50 minus 30, that means 20 milliampere. So this will be the minimum current which will flow through this load resistor, and from this we can say that the maximum value of the load resistor will be equal to Vz divided by IL minimum, that means 5 volt divided by 20 milliampere. So the maximum value of the load resistor will be equal to 250 ohm. So from this we can say that for the given parameters, when the value of load resistor is in between 100 ohm and the 250 ohm, then the given circuit will work properly as a voltage regulator. So now we will assume that this series resistor Rs and the load resistor RL are constant, and this supply voltage Vs is variable. So we will find the minimum and the maximum value of the Vs such that the Zener diode will work properly in the breakdown region. Or in other words, this circuit will work properly as a voltage regulator. So first of all, we will find the minimum value of this supply voltage. And for that, once again, let us write down the Thevenin's equivalent voltage which appears across the Zener diode, that is equal to Vs times RL divided by Rs plus RL. Now from the expression, if you observe, as we reduce the value of this Vs, then the Thevenin's equivalent voltage which appears across the Zener diode will reduce. And if it goes below this Vz, then the Zener diode will come out of the breakdown region. So the minimum value of this Thevenin's equivalent voltage should be equal to Vz. And from this we can find the minimum value of this supply voltage. So the Vs minimum will be equal to Rs plus RL divided by RL times Vz. So this will be the minimum value of the supply voltage which will ensure that the Zener diode will work in the breakdown region. Similarly, now let us find out the maximum value of this supply voltage. Now here if you observe, as the Zener diode is operating in the breakdown region, so the voltage at this node will be equal to Vz. That means the load current IL will be equal to Vz divided by RL. Now here, as this Vs is variable, so as we increase the supply voltage, then the source current Is will increase. And here the source current Is can be given as Vs minus Vz divided by Rs. So from the expression we can say that as the value of Vs will increase, the source current Is will increase. But here, as this load current IL is fixed, so the remaining current will flow through this Zener diode. So as we keep on increasing the value of Vs, the current which is flowing through the Zener diode will increase. But we know that the maximum allowable Zener current is equal to IZM. So this will limit the maximum value of this source current. Or in other words, we can say that the Is max will be equal to IZM plus IL. And from this Is max, we can find the maximum value of this source voltage. That means the Is max will be equal to Vs max minus Vz divided by Rs. So in this way, we can also find the maximum value of the supply voltage. So based on this, let us take one example. And in this example, we have been asked to find the minimum and the maximum value of the supply voltage such that the Zener diode will work properly in the breakdown region. So first of all, let us find out the minimum value of this supply voltage. And this minimum value can be given by the expression Vz times Rs plus RL divided by RL. And if you put the value of Vz, Rs and RL, then we can write this expression as 10 volt multiplied by 100 ohm plus 500 ohm divided by 500 ohm. And if we simplify it, then the minimum value of the supply voltage will be equal to 12 volt. So this 12 volt will ensure that the Zener diode will work in the breakdown region. Similarly, now let us find out the maximum value of this source voltage. Now to find that value, first of all let us find out the load current, that is equal to Vz divided by RL. And here Vz is equal to 10 volt and RL is equal to 500 ohm. That means the IL will be equal to 20 milliampere. Now here we have been given that the IZM is equal to 25 milliampere. That means the Is max will be equal to IZM plus IL, that is equal to 25 milliampere plus 20 milliampere, which is equal to 45 milliampere. And from this we can find the maximum value of this source voltage. So we can write this expression as Is max is equal to Vs max minus Vz, that is 10 volt divided by 100 ohm. And here the value of Is max is equal to 45 milliampere. So if we simplify this expression, then the value of this Vs max will come out as 14.5 volt. So this will be the maximum value of the supply voltage. So for the given Zener regulator, whenever the supply voltage is in between this 14.5 volt and the 12 volt, then this circuit will work properly in the breakdown region. Similarly, now we will assume that the supply voltage Vs and the load resistor RL are constant and this series resistor Rs is variable. So here we will find the minimum and the maximum value of the Rs such that the Zener diode will work in the breakdown region. So first of all, let us find out the maximum value of this series resistor. And to find that, once again, let us write down the expression for this Thevenin's equivalent voltage, which is equal to RL divided by RL plus Rs times Vs. Now if you observe over here, as we increase the value of Rs, then the Thevenin's equivalent voltage will reduce. But this voltage should be at least equal to Zener voltage, such that the Zener diode will not come out of the breakdown region. And from this, we can find the maximum value of this Rs. So if we equate this term with Vz and if we rearrange it, then the maximum value of this series resistance Rs will be equal to RL times Vs minus Vz divided by Vz. So this will be the maximum value of the series resistor. Similarly, now let us find out the minimum value. Now here, as the value of load resistor RL is fixed, so the load current IL will also remain fixed. And this load current IL will be equal to Vz divided by RL. Now here, this source current Is can be given as Vs minus Vz divided by Rs. So from the expression, as we reduce the value of Rs, then the source current Is will increase. So if we keep on reducing the value of Rs, then the value of Is will increase. But here, as the IL is fixed, so the remaining current will flow through this Zener diode. And we know that the maximum allowable Zener current is equal to IZM. So that will limit the minimum value of this Rs. So we can say that this Is max is equal to IZM plus IL. And from this Is max, we can find the value of this minimum series resistor. That means Is max is equal to Vs minus Vz divided by Rs minimum. So in this way, we can also find the minimum value of this series resistor. So based on this, let us take one example. So in this example, we have been asked to find the minimum and the maximum value of the Rs such that the Zener diode works in the breakdown region. So the maximum value of this series resistor Rs can be given as RL times Vs minus Vz divided by Vz. And if you put the values, then the Rs max will be equal to 1 kilo ohm times this Vs minus Vz is equal to 10 volt and Vz is also equal to 10 volt. That means the maximum value of this series resistor will be equal to 1 kilo ohm. Similarly, to find the minimum value, first of all let us find out the load current, which is equal to 10 volt divided by 1 kilo ohm, and that is equal to 10 milliampere. Now here we know that the maximum allowable Zener current is equal to 40 milliampere. So from this we can say that this Is max is equal to Izm plus IL, that is equal to 50 milliampere. And from this we can find the minimum value of this Rs. That means this Is max will be equal to 20 minus 10 divided by Rs minimum. That means Rs minimum will be equal to 10 divided by 50 milliampere, which is equal to 200 ohm. So from this we can say that for the given example, whenever the value of this series resistor is in between the 200 ohm and the 1 kilo ohm, then the circuit will work properly as a voltage regulator and the Zener diode